Let's jump right in. And I decided to pick up with an example that I was working on during the recorded lecture from yesterday. So if you've watched that video, you'll know the last example I'd left a little bit unfinished. And so I'm going to pick up with that again. Let's read through this problem. It says, we assume that 13% of the population is left-handed. I'm giving a lecture in a 300-seat auditorium, and it has 25 lefty seats. That should read lefty seats. In a class of 135 students, what's the probability that there will not be enough seats for the left-handed students? You may assume that the normal model holds for the sample proportion. So we will circle back around to checking the conditions for the normal model, but going into at least this example, we will assume that the normal model holds for the sample proportion. Now let's take the problem and unpack the different quantities that are being stated here. Firstly, it says 13% of the population is left-handed. So in the population, in this problem, if we define a success to be that someone is left-handed, then we know the proportion of left-handed people in the entire population is 13%, or as a decimal, we can express that as 0.13. And remember the notation, lowercase p on its own refers to the population proportion. Now this lecture I'm giving, it's taking place in a 300-seat auditorium, and there are 25 seats that can accommodate left-handed people. But I don't have a full 300 people showing up. I have 135 students showing up for this lecture. And so I want to know, what is the probability that there will not be enough seats for the left-handed students? So the fact that the auditorium seats 300, that's actually irrelevant here, because I just care about, out of my 135 students, do I have enough seats for left-handed? So in my sample, the potential for having too many left-handed students would be the following. So in the sample, if I have 26 or more, right, that would be when I run into a problem here. Now, what is that as a proportion? This is now something calculated in a sample, and my sample proportion is p hat, and this would be if 26 of the 135 were left-handed. That's when I would have a problem. And if I express this as a proportion, I get 0.192. So remember to keep track of the notation here. P on its own refers to a quantity in the population. We know if we look at all people in the world, 13% are left-handed. But if I consider the people showing up for the lecture, the 135, to be my sample, if 26 or more of them are left-handed, then the auditorium can't accommodate them. And I can express that as a proportion to the proportion in the sample I call p hat. Now, we now want to calculate what is the probability, or how likely is it that I do not have enough seats. And this requires knowing the mean and the standard deviation of the normal model. So for this normal model, we need to determine what the mean and the standard deviation are. Now, the mean of the normal model will always be p, the population proportion. And the standard deviation, this is the quantity we call sigma p hat, And the formula for that quantity is the square root of P times Q over N. And P is 0.13. Q is 1 minus P, which in this instance is 0.87. And my sample size would be the 135 students. So if I plug all of that into my calculator, I end up getting 0.029. So what I know here is that I am working with a normal model, N for normal. It has a mean value, or the peak of the normal model is at the value 0.13, and it has a standard deviation of 0.029. So let's see, it may have a question here. I have to circle back around to that question because I think I may have done the problem in the video slightly differently, but let's just talk through where I'm getting the 26 from here. I want to know what the probability is that there will not be enough seats. If there are 25 who are left-handed, then I do have enough seats. It's only if there are 26 students that show up that I do not have enough seats. So if I did that differently in the video, it should have been 26 in the video as well. And so I hope that doesn't cause too much confusion for anyone. Also, just making sure everyone knows where the numbers in the standard deviation come from. The Q in the formula, the Q is equal to 1 minus P. So in this case, 1 minus the 0.13, that's where I get the 0.87 from. So we now want to calculate what the probability is, and I'm using a capital P here for probability. What the probability is that P hat is at least 0.192, because that's when I'm going to have a problem. If my sample proportion is 0.192 or larger. But I want to express this in terms of a z-score. I want to figure out what the equivalent is as a z-score. Now my z-score formula, when working with a proportion, is given by p hat minus p divided by sigma, which is the standard deviation. So in this case, it's 0.192 minus 0.13 divided by 0.029. And if I do that calculation, I get 2.14. So my original problem expressed as a proportion is that p hat is at least 0.192, but expressing that in terms of a z-score, I can calculate it as what's the probability that my z-score is at least 2.14. Now, the advantage of expressing it as a z-score means I can now go and consider the problem on my bell curve. My standard bell curve, which is centered at 0, so in the right here, I have this value 2.14. And remember, I am trying to find here what the chance is that I have a z-value of 2.14 or larger. So this is where my standard normal table comes in. And I will upload a copy of this to D2L in case anyone doesn't have one. But I am now going to look up this number 2.14 in my z table. So on your z table, on the row, you're going to find 2.1. The second decimal place is 4, so find that as well. And so now I'm just checking where do the row and the column meet up. That's the entry I want from the table. And you only have to care about the first 3 decimal places. So you'll do some appropriate rounding, but to 3 decimal places, this value is 0.984. Now, what's important to remember is when you look up something in the normal table, that tells you what the value is to the left of the reference value. So I looked up 2.14, and my Z table is telling me there is a 98.4% chance of being below that Z score. But I want to know how likely I am to be above the Z score. So this would be 100% minus the 98.4%, which in this case is 1.6%. So the chance is 1.6% that I have too many left-handed people show up and the auditorium cannot accommodate all of them. So I'll pause here for a few seconds in case someone has a question. If you want to speak and you're on a computer, you can hold down spacebar and talk, or I'll wait a little bit in case someone needs to type a question into the chat feature as well. Okay, someone is asking in this problem where I got the 0.192 value. So that's my sample proportion. And this specifically came from asking myself, when would I not have enough seats that are suitable for left-handed people? If I had 25 people show up, I would be fine. Right? There are 25 seats that are set up for left-handed people, but if I had 26 or more show up, it would be a problem. So in the class of 135 students, if 26 or more were left-handed, I would have a problem. So what's that as a proportion? 26 divided by 135 gives me the 0.192. That's where I found the value 0.192. Okay, let's move on to the next example. And the setup will look familiar, but the questions being asked here are different. But we had a similar setup to a problem in our previous live session. So in Texas, 21% of vehicles on the road are manufactured by Ford. Let's assume that a researcher plans to take a sample of 110 randomly selected vehicles in Texas and record the proportion that are Ford. So the 0.21 or 21%, which I can express as 0.21, that's my population proportion because that applies to all vehicles in Texas. And then I'm going to take a sample of 110. So once I express anything in terms of the sample, if I calculate a proportion relating to those 110 vehicles, that would end up being p hat. Now, first part of the question here says we want to verify the conditions for the normal model to hold. There are 4 conditions outlined in the lecture, but there are only 3 conditions that you can really check in practice. And so you want to run through these and make sure that they are met. The first condition is independence. You want to either verify or state clearly that you are assuming all the vehicles in your sample are independent of one another. So I'm not going to my neighbor's house who I know has 5 Fords and putting all 5 of those in my sample, because if I'm getting 5 vehicles owned by the same person, I don't have that independence. Each vehicle included in my sample needs to be independent of every other vehicle in my sample. So we need to assume independence. Secondly, we want to check whether the 10% condition holds. Now, this condition says my sample size cannot exceed 10% of my population size. Population size would be all vehicles in Texas. And how many vehicles do we have on the road in Texas? Several million. So if I have a population of several million and I'm sampling 110, that's definitely far less than 10%. So the N of 110 is much smaller than 10% of the millions of vehicles on the road. And our last assumption is the success-failure condition. So here, you have to do a little bit of math. You have to calculate n times p, and you have to calculate n times q, which is the same as calculating n times 1 minus p. So n is 110, p is 0.21. And so if you multiply 110 and 0.21, that gives you 23.1. And if you multiply 110 and 0.79, which I get by taking 1 minus 0.21, this gives me 86.9. And the condition says both of these values have to be at least 10. If each of those values is at least 10, then the normal model applies. So if you get asked whether the normal model applies, those are the 3 components that you have to address. Now, next, we want to calculate the mean and the standard deviation for the normal model. The mean is always going to be P, the population proportion. And the standard deviation, that's the sigma quantity. That formula is always P times Q over N. So in this case, it's 0.21 times 0.79 divided by sample size of 110. And if you go and plug all of that into your calculator, you will get 0.039. So the normal model I'm working with here, the peak of the bell curve is at 0.21, and it has a standard deviation of 0.039. The last part of this problem, part C, then asks, calculate the probability that the sample will include 20 or fewer Fords. Right, so what proportion does that correspond to? Well, that means 20 of my 110 sampled vehicles. That's where I get my sample proportion. And if you calculate this, I'm just rounding to 3 decimal places here, I get 0.182. So I want to know how likely is it that my sample proportion is 0.182 or less, right? I want to calculate the probability that p hat is less than or equal to 0.182. Now, again, I want to convert this to a z-score. So let's do our z-score calculation. Z is defined as p hat minus p divided by sigma p hat. So p hat, my sample proportion, is 0.182. P, my population proportion, is 0.21. And sigma, my standard deviation, is 0.039. And so I plug all of that in, and if I do that calculation, I get negative 0.72. So I am trying to figure out if I again visualize a standard normal bell curve centered at 0, then to the left here I have the value negative 0.72, and I'm trying to figure out, if I look at this bell curve, how much of the probability is to the left of that value. So again, I'm going to use my standard normal table here, but now I'm going to look up negative 0.72. So let's flip back over to the normal table. Going to find here negative 0.7, and the column 2, column 0.02. So if I combine those, I have negative 0.72. And so I just want to see where these meet up. And in this case, it gives me a value, if I round it to 3 decimals, 0.236. Let me just change the pen out here. So 0.236. That's the probability to the left of the value, or the probability less than or equal to that specific value. And that's already what we wanted here. Less than or equal to means to the left. So in this case, I have my solution. It's 23.6%. I could use the value from the normal table directly. So just pay careful attention. If you let me scroll up here for a minute. In our previous example, we had a greater than or equal to, and that meant that we wanted to find the probability to the right of our z-value. The table always gives us area to the left, or probability to the left, and so we had to subtract it from 100. But in the problem we just did, we had a less than or equal to, which means we wanted the probability to the left of our z-value, and that's the way the table already gives it to us. So we were able to use it directly in this instance. So if anyone has a question, you're welcome to ask now, but I will say example 3 is going to be something very similar to 2. So it may be helpful to hold on your question for a minute, because we'll work through one more example carefully looking at this exact same method of calculation. But I'll wait a few seconds in case someone has a question. Okay, example number 3. In Fort Worth, 82% of college students eat at Chipotle at least once a month. let's assume that a researcher plans to take a sample of 57 students in Fort Worth and record the proportion that eat at Chipotle at least once a month. So when we're talking about all college students in Fort Worth, that 82%, that's my population proportion because it applies to all college students in Fort Worth in totality. Of all of those students, I'm going to take a sample of 57. And in that sample, I'm going to record what proportion eats at Chipotle at least once a month. So first, we want to start off by verifying the conditions for the normal model. So we'll have the same three conditions: independence, 10%, and success failure. We want to check these three conditions. Now, if you see the word randomly is often a kind of surrogate word for independent because it means they're not chosen in any systematic kind of way. So independence can reasonably be assumed because we're doing this random selection. The 10% rule, well, the question would be, how many college students are there in Fort Worth? I know that TCU is not the only school, but even if we just looked at TCU, we have about 10,000 students, and 10% of that would be 1,000. So if our sample was like around 1,000, we would be potentially in trouble. But the 57 is much smaller than 10% of all college students. So 10% rule is definitely met. Success failure, this is where we have to do a little bit of math again. We have to calculate n times p, and we have to calculate n times 1 minus p. So 57 multiplied by 0.82. If you do that calculation, you will get 46.74. And n times 1 minus p, so 1 minus the 0.82 gives me 0.18, and that gives me 10.26. Now, one of them is close, like one of them is barely above 10, but since both numbers are above 10, the condition is met. So the normal model will hold because all three of my conditions are assumed. Then, if I'm using the normal model, what is the mean and the standard deviation of the normal model? Well, the mean is P, the population proportion. The standard deviation, I just have to go and calculate using that value for P. So 0.82 times 0.18 divided by sample size of 57. And if I do that calculation, I get a sample proportion, or sorry, standard deviation of 0.051. So my normal model centered at 0.82 and standard deviation of 0.051. All of this I then want to use to do part C, where I calculate the probability that the sample includes 50 or more students who eat at Chipotle at least once a month. Now, what's that as a proportion of my sample? If 50 of the 57 students eat at Chipotle once a month, that's the reference proportion. And if you do that calculation, that's 0.877 as a proportion. So 50 or more, I want to calculate therefore the probability that p hat is 0.877 or greater, because the or more tells me it's greater than or equal to. I want to convert this to a z-score problem. So let's do our z-score calculation here. My z-score is p hat minus p over the sigma quantity. And in this instance, it's 0.877 minus 0.82 divided by 0.051. And that is equal to 1.12. So that's the reference z value that I'm working with here. Now let's visualize this again on a bell curve. My bell curve is centered at 0. I have this reference value 0.12 here, and I have a problem with a greater than or equal to, so that means I want to find the probability to the right of that value. I can use my normal table, but the normal table by default gives me the probability to the left. So we're going to look up 1.12 in our table. Let's find that here. 1.12. That gives me to 3 decimals 0.869. Remember, that's the probability to the left. Probability to the left is 86.9%. But I want probability to the right, so I have to subtract it from 100, which in this case ends up giving me 13.1%. So that is the probability that there are 50 or more students in my sample who eat at Chipotle at least once a month.